Instead of taking our course on handling data with Nondetects, why not just substitute 1/2 the detection limit for Nondetects? Well, what's wrong with substitution? First, substitution produces what I call invasive data. It's data that is not natural to the system of concentrations that are actually in the samples that you've collected. It adds a pattern to those data. By putting the same number in multiple times, it adds a pattern to the data that you probably do not intend to add. It is not a neutral process. Substitution produces, as a result, poor estimates of things like standard deviations. It produces poor results for statistical tests and regression. And then finally, there are far better methods that exist right now. They work well. They largely come out of the medical statistics community. They've been around, some of them, since the 1950s. And you really don't need a PhD to do them. So there are good, in fact excellent, alternatives that you or your employees could use to handle data with Nondetects. For more detailed information than what this short video is going to talk about, you could subscribe to our Nondetects and Data Analysis course that is located on our training site at practicalstats.teachable.com. And there's much more in that. I'm going to give you an overview to see what is available that can be done with data for Nondetects. So here's just one example. Why not substitute? Here's what's going to happen if you do. So these are 3 groups of data. Their reporting limits are at 1 through 5 micrograms per liter. So there were 5 different reporting limits. And about 80% overall of the data have been censored below 5. So about 80% are below 5. There's about 20% of the data in the high density residential group above 5. There's about 10% of the data, including that outlier, above 5 in the medium density residential group, and there are no data above 5 in the low density residential group. So the question is, do these 3 groups all look the same, or is their pattern different in the 3 groups? Could I detect that there's a difference between them? If you substitute in, let's say, 1/2 the detection limit, so that all the less than 5s and all the other data below 5 were put at a value of 2.5. You get a p-value of 0.56, which means there's no difference. We cannot see a difference. If you substitute in 0 instead, same result. If you substitute in the detection limit instead, same result. Any number between 0 and 5. If you like 0.7, some people use 1 over the square root of 2. It's about 0.7. Same difference. There is no difference between these 3 groups. However, if I used one other very simple test called the Kruskal-Wallis test, a non-parametric test, and here what I would do would be to set all of the data below 5, all the less than 4s, 3s, 2s, and 1s, all the detected values that are below 5. So there may have been some detected 3s and 4s when the detection limit was 1. All of those data get set as less than 5. They're ranked so that they are the lowest ranked data. And then all of the data that you see as circles here are values that will get the exact same ranks they would have had if you knew what the values were for all of these lower data. Run a ranked-based test, the Kruskal-Wallis test. The p-value is small, 0.01. It says you would not get this kind of differentiation between the groups more than 1 out of 100 times. So that's unusual enough that we would reject the null hypothesis and say we can see a difference between these 3 groups. There's definitely a difference in how likely you are above 5, depending on which group you're in. So there are very simple tests that you would learn about in that course, like this: setting all the data below the highest detection limit to be the same and run a non-parametric test. There are also Other tests that, again, come out of the survival analysis literature. This is also a non-parametric test using multiple detection limits, so you don't have to set less than 4s to be different than less than 5s, or a detected 3 to be different than less than 5s. It will adapt to those. And it's called the Pareto test. And we cover it and how it works in our Nondetects and Data Analysis, or NADA, course. The command to do it is send one way in the software that comes with the class. And you put in the concentration column the indicator of whether it's below or above. So values that have an indicator of 1 are less thans. And then the grouping variable, density. So you get this table, which gives you the outputs of the means and standard deviations. Does the Pareto test, which is a non-parametric test with a test statistic and a p-value that is very small, 0.00029, which tells you that these groups are different. The land use groups are different. It actually also gives you some pairwise comparisons, so you can see which are different from the others. The only ones that cannot be distinguished are the low data, the low column, to the medium group. That's a p-value of 0.27. So for these others, we can see that high is different than low and high is different than medium. All of this is done without substituting in numbers, and it's certainly available right now for your employees. There's a lot of confusion still over the value of Nondetects. I wrote a paper back in around 1990 arguing that we should use these better methods. This is in the same journal, actually, Environmental Science and Technology, just written last year. It was an opinion piece rather than a published article. It's by Ronald Heitz. Dr. Heitz is one of the environmental chemists that I respect the most. He's really done an amazing job in the analytical chemistry for measuring low-level contaminants, especially organics. But at the end of this opinion piece, he makes a statement that anytime you have a percent of Nondetects greater than 20%, for whatever reason, it's unlikely that the data can give useful results. Well, that's in fact not true. We just saw an example where there was overall about 80% censored, and we could still distinguish between the groups, just as we could have if we had had all of those numbers down below 5. If you use good procedures that are designed for what statisticians call censored data, data above a threshold or below a threshold, here below detection limits, you can do a lot with that type of data. The big signal here is it's 0% above 5 versus 10% versus 20%. And that's a big difference. And so the p-value is very small. If you substitute in data, you get these patterns that don't make a lot of sense. So for example, here's the original data, had a standard deviation of 1.02. Then if I took all the less than 2s, all the values in this data set that were less than 2, and set them to be half a 2 if the detection limit was at 2. So some of the numbers were above 1. Some of the numbers were below 1. They all get called a 1 because it's half the detection limit. You get this box plot over here where it's flat right at the bottom. There's all these 1s for the data that were less than 2. What you get is a standard deviation of 0.84. The standard deviation is really, in a lot of ways, a more important statistic. It's the variability of the data set. Well, if you take a good portion of the data and put in the same number all the time, you're really lowering the variability. And that standard deviation is used in things like t-tests, analysis of variance, regression, and a lot of different statistical procedures. It's used for just computing intervals, for example. So what about substituting and then computing a confidence interval? Singh and others in 2006 stated that when you were trying to compute the UCL 95, a one-sided confidence limit on the mean, that putting in a half the detection limit does not provide adequate coverage, meaning that the limit is not high enough, that the interval is not wide enough, even for as percent detects as low as 10%. So with substitution, a low fraction really would be resulting in a not useful procedure. So if that's what Dr. Heitz had intended to say, then I would agree with him entirely. That with substitution, you really can't get much back out because you're putting in a signal that's not there. The lower standard deviations produce lower limits, too short intervals. So their recommendation was do not use 1/2 the detection limit to compute a UCL. And there are better methods, and we talk about those in the course. What about regression? Here's some data that show a nice linear pattern, straight line pattern. It had a true correlation coefficient, Pearson's R, of 0.81. When we do substitutions, there were 2 detection limits at 3 and at 1, so all the less than 3s got 1.5, all the less than 1s got 1/2, and you see these flat lines. That's a pattern. So stop thinking about substitution in terms of an individual value. Oh, it's halfway below the detection limit. That must be as good as anything else. You're putting in the same number all the time, and so in this case, it's a flat, zero slope line. That's going to lower the slope. When you compute a regression, it's going to lower the correlation coefficient. Here it went from 0.81 down to 0.55. And the tragedy is that there are much better methods. And so in terms of regression, here was another paper in ES&T back in 2003 by Thomas and Nelson that showed that when you do substitution in one regression, you get biased slopes. They are too close to 0. And you get small standard deviations around the line. That's called the standard error of the regression. Those are too small, so that indicates that you have significant tests, and you would bring in explanatory variables, X variables, that should not be in the regression. Those are the consequences of substitution. That's why you should not do it. And then, of course, the final reason you should not do it is because they're far better things. So here is the procedure to do correlation and regression with censored data that have multiple detection limits are fine. This is relating the concentrations of lead in blood. And here's the indicator of censoring, 1 or 0. It's either a non-detect or it's not, versus an X variable. That's the lead in kidneys. Here's correlation coefficients. The likelihood R correlation. There are these correlation coefficients that are used for censored data. The one in the middle here, the rescaled likelihood, is the one that I tend to use. And it's the closest to Pearson's R, and it's here 0.87. So you can compute that with data that are non-detects and not substitute in a number for them. You can also get back this regression equation. Here's the intercept. Here's the slope on the kidney lead concentrations. This was in log units, so down here you'd write it out as the log of blood lead. It was minus 4.4 plus 2.4 times kidney lead, or translate that back into the original units. You get a test statistic on that and a p-value. So it works very well. You can plot those results. Here's something that was a linear relationship in log units for the blood lead, and when you bring it back, it's a curve. Notice the non-detects here, so you can plot data with non-detects along with the data that are detected. Those non-detects here are represented by dashed lines coming up from the bottom. There's an important signal in this with the non-detects, and that is included in these good methods, these newer methods. And that is that, look at where all the non-detects are. They're all at the low lead in kidney levels. You don't see them out here. So it's more evidence that as the lead in kidneys increases, also the lead in blood increases. And so this information related to these dashed lines is also included in these types of procedures. Here's one of the classic problems with substitution. Here's data that I generated to have no trend at all, no change over time. So it's just a flat line with noise. And what we're going to do is replace some of the smallest values and call them non-detects. So if they originally were something like, what does this look like, about 0.08, so maybe it was 0.16 as the detection limit, and the number was below 0.06, so it became a less than 0.06, and then someone put in 1/2 the detection limit at about 0.08. And then the detection limits went down over time. That's a very typical pattern in laboratories, and it's generally a good thing that detection limits can decrease over time, but not if you're going to put in 1/2 or some other fraction of the detection limit. And so these numbers go down over time. And you're putting in a signal there, a downtrend, that is not what's back in the original data. So those decreases over time may test as significant, and you have a significant downtrend when there really is not one back out in the field. Alternatively, you could use a good piece of software. Here's the SEN-CKEN, the censored CKEN for the seasonal candle test procedure that handles non-detects, even if they're at multiple detection limits without substituting in data. It's part of our course. So it's looking at whether chromium changes, it looks like, over time, and it's split by seasons. You can find that the dry season, there's a downtrend. The slope is significant. Here's the p-value for it. Here's the slope itself. There's no trend in the wet season. Overall, there is a significant trend. You can do all of that. You can plot that trend, that overall trend. Here's the downtrend in the data. These are things that you could not see with substitution. If you're doing regression, you can do things like QQ plots, probability plots, things that test for whether the data have a normal distribution, or in this case, the residuals from the regression have a normal distribution. You can do all of that for data with non-detects. So our course covers things including all manner of parametric and non-parametric methods, including just computing mean standard deviations. How do you do that? Confidence, prediction, and tolerance intervals for data with non-detects, plotting data, as you've seen, comparing data to standards, testing differences between two groups, kind of like a t-test sort of approach or a rank sum test, the 3+ group tests that we saw earlier with that TCE data. We've seen just a little bit about regression and correlation and trend analysis. There's also some multivariate methods in the course, and all of these methods are for data where you do not have to substitute in numbers like 1/2 the detection limit for non-detects and put in a signal or a not signal, a flat line. That is not what's in the data. You can avoid that completely. There are some videos that are free on our training site that you or your employees could go to see. And so you could let other colleagues know about those. How methods for non-detects work, that's called the mystery of non-detects. So you can learn how these procedures generally work and so on. So there's information in these videos, but there's a lot more in the course. So thank you for viewing. If you have any questions, you can certainly write to me, send me an email, and I'd be glad to answer that. You can find those courses and the free recordings to view at practicalstats.teachable.com. Thank you very much.